In this video, we'll be learning how to solve exponential equations, but this video is going to focus on how we can use our knowledge of logarithms and the relationship between logarithms and exponentials to solve these types of equations. So the last strategy here that we're going to use is a strategy that we use when we can't get common bases on both sides. So here we have a 2 and we have a 5. And there's no way we're going to get a common base for 2 and 5. So what we can actually do here is we can use our knowledge of inverses. So we know that, if we have an exponent of 2, so say we have an exponent of 2, we know that its inverse deals with a log of base 2. And we're going to use that to our advantage here because we can actually undo exponents by using its inverse. So if you can get the exponent alone, what you can do, just like where you can square root both sides or square both sides to undo, squareds or roots, we can do the same thing with an exponent. So here we have an exponent of 2 to the power of x. And my goal is to solve this equation. And I notice that I can't get common bases, so I can't just set the exponents equal. What I can do here is I can actually undo that exponent by using log base 2. So what I'm going to do here, because I have an exponent with a base of 2, is I'm actually going to take log base 2 of each side. So I have log base 2 of each side. Okay? Now we've learned previously that if we have log base 2 and exponent base 2, they undo each other. So by taking log base 2 of each side, we're left with just x on the left-hand side. Then on the right-hand side, yes, I do have log base 2 of 5, but we now know how to evaluate logarithms of any type using our change in base formula. So by taking log base 2 of each side, I was able to get x out of the exponent basically because I was able to undo that exponent base. Then from here, we need to use the change of base formula. So I'm going to turn this into a logarithm of base 10. What's inside goes in my numerator, so that's 5, divided by the logarithm of my base in the denominator, which is 2. So I can now take log of 5 divided by log of 2. Remember, both of those logarithms are base 10. And if we divide them in our calculator, we find that x is approximately 2.32. So again, we can use our knowledge of bases here, of a base 2 log and a base 2 exponent, to undo that exponential base so that we can basically take what's in the exponent out of the exponent. So let's try a couple of examples here. This first one, I noticed that I have an exponent of base 5 by itself on the left-hand side and 8 on the right-hand side, which I know I can't get common bases for. So in order to undo that exponential base of 5, I'm going to do log base 5 of each side. In doing so, log base 5 and an exponent of base 5 undo each other. So I'm left with x plus 2 is equal to log base 5 of 8. I can then use the change of base formula on the right-hand side. So I can do log of 8 divided by log of 5 to figure out what's actually on the right-hand side here. So if I take log 8 divided by log of 5, I end up with about 1.29. And then in order to get x alone, I just need to subtract 2 from each side. So I end up with x is approximately negative 0.71. If we look at the second example here, we can see that we have an exponent with a base 7 alone on the left and then 10 on the right. There's no common base that exists. So we're going to use log base 7 to undo that. By taking log base 7 and exponent base 7, we can undo those and we're left with 2x minus 3 on the left and then log base 7 of 10 on the right. We then use our change of base formula. So we have log 10 over log 7. So we take log 10 over log of 7, which is about 1.18. We then are going to solve this like a normal little equation. So we add 3 to each side. So we end up with 2x is equal to 4.18. Divide that by 2. We end up with an x value equal to about 2.09. Now if we look at the bottom two equations, what I notice in both of these equations is that the exponent is not by itself. We can only use this logarithm trick when the exponent is completely by itself on one side of the equation. So for this one here, we're going to need to subtract 3. So we have 4 to the power of x minus 5 is equal to 12. And then from here, we can use that logarithm trick to undo that exponent base. So we're going to do log of base 4 to undo the exponent, log of base 4 on this side as well. The bases undo each other, so we're left with x minus 5 is equal to log base 4 of 12. We then use our change of base formula, so we have log 12 over log of 4. If we take log 12 over log of 4, we find that we approximately have, let's see, x minus 5 is equal to 1.79. We then add 5 to each side, so we end up with x is about 6.79. Finally, in example 4 here, remember, again, we need to get this exponent base by itself. Until we have that, we can't use that little exponent trick. So I'm going to add 7 to each side to start. So I have 8 times e to the power of 0.5x minus 2 equals 32. Divide both sides by 8, so I have e to the power of 0.5x minus 2 is equal to 4. Now from here, remember, to undo e, we need to use the natural logarithm because that has a base of e. So we're going to take the natural log of each side. So by doing so, the natural log undoes that e there. So I have 0.5x minus 2 is equal to natural log of 4. What's really nice here is I don't have to use the change of base formula because I can calculate natural log of 4 on my calculator. So if I have natural log and I put 4 on the inside, I find that that's approximately 1.3, we'll do 1.39, round to 2 decimals. We then need to add 2 to each side, so we have 0.5x is equal to 3.39. Then divide by 0.5. And we end up with x is approximately 6.77. So we're able to use our knowledge of the fact that logs and exponents are inverses of each other in order to solve these equations and actually undo those operations. And all of these x values that we found, all 4 of them, if you were to plug them back into the original equations, they would make that original equation true.